Lighthouse Scientific Education presents a lecture in the Atomic Structure series. The topic, Basics of the Atom, with atomic and mass number. Material in this lecture relies on an understanding of the previous lectures, order and matter, and history of the atom. We will begin our discussion of the basics of the atom with a description of subatomic particles, paying particular interest to mass and charge. This is followed with a look at elements and the periodic table of elements. Important values in this table include the atomic number and the mass number. We will test our understanding of the basics of the atom with some practice exercises. We begin with an overview of atomic structure. Almost all matter, at least on this planet, is comprised of atoms. Atoms are composed of three different subatomic particles. Subatomic indicates that the size of the particle is less than that of an atom. These are protons, neutrons, and electrons. We will describe these three subatomic particles in some detail. As you might know, atoms come in different forms or types. The difference is in how the three subatomic particles combine in the atom. These different types are called elements. Elements are a type of matter, and atoms are a particular particle of that element type. Atoms and elements can sometimes be confused, and we will clarify that distinction shortly. But first, let's review the characteristics of the subatomic particles. We can compare and contrast subatomic particles by looking at their relative mass, their charge, and their location in the atom. We have the proton, the neutron, and the electron. They have shorthand symbols. For the proton, it's P with the superscript plus sign. For the neutron, it's just N. And for the electron, it's E with a superscript minus sign. The first of the two major properties of subatomic particles is mass. Mass is usually given in atomic mass units, or AMUs. Since these subatomic particles are so small, a special mass unit is used. The AMU is based on the mass of the proton, which is 1.660 times 10 to the minus 27 kilograms. As it serves as a definition of AMU, it should be no surprise that the mass of the proton is 1 AMU. The neutron has a very similar mass. It is only slightly larger at 1.0007 AMUs. The electron, however, is much smaller. It weighs 1/1837th as much as that of a proton. Its mass will generally not be considered when summing up the mass of the atom. That doesn't mean that it doesn't have a mass. It's just that it's so small that it can be neglected in the calculation. The other major property of the atom is charge. The charge on a proton is +1. The neutron has no charge. It is neutral, 0, as its name suggests. The charge on the electron is -1. While mass is a property that we are all familiar with, charge is not. We will not concern ourselves too much with the physical explanation of charge. We'll have to settle with a physical description. Consider the static electricity that can be generated when passing a comb through one's hair. That is a distribution of positive and negative charge. Then there's the electricity that runs through our home. That is negative charge in the form of electrons. What we want to know about charge is that positive and negative charges attract each other. And positive and positive, or negative and negative charges, repel each other. Another important aspect of charge is that in the atom, the number of protons is equal to the number of electrons. What this means is that while the atom has charged particles, it doesn't have a net or final charge. We will explore this more in detail in the Ions and Isotopes lecture. The last description of our subatomic particles is their location in the atom. Where are these particles found? For the proton, it is in the nucleus. Nucleus means central. It is the center of the atom. The neutron is also in the center of the atom. The electron, however, is located or found outside the nucleus. Let's put this description together and sketch out an atom. As said earlier, almost all matter is composed of atoms. This cartoon shows atoms packed together in a solid material. Individually, the atom as a whole is spherical. The protons and neutrons are located at the very center in a densely packed core called the nucleus. If an atom were the size of a football field, the nucleus would be about the size of an apple. The nucleus makes up a very, very small portion of the atom. It is, however, where the vast majority of the mass resides, since the remaining particle, the electron, these guys are zipping around the nucleus and have only a tiny fraction of the mass of the other two particles. The next step in building an atomic understanding of matter is what are the different atom types. And for that, we use the chemistry student's best friend, the periodic table of elements. Earlier we noted that atoms come in different forms or types. And these types are called elements. An example of element is hydrogen. It is made up of hydrogen atoms. The element is the type of matter, and the atom is a particle of that type. The element carbon is made up of carbon atoms, and the element oxygen is made up of oxygen atoms. So, elements are types of matter, and atoms are particles of that element type. Clear this distinction up in your mind, and you will prevent a fair amount of confusion. There are unique features that all periodic table of elements contain. We will use this imaginary element X as a demonstration. In the table, each element gets its own symbol. Previously, we saw that carbon was represented by C and oxygen by O. There are also two important numbers for each element. The number at the top is called the atomic number. Some books call it the Z number and use it as the charge of the nucleus, since it represents the count of positive charge. And, importantly, it is also the mass of protons in AMU, since the mass of a single proton is 1. We will definitely be making use of this fact. Additionally, we know that in an atom, the number of protons equals the number of electrons. Therefore, the atomic number will also tell us how many electrons there are in the atom. When we get to ions, we will see that this proton-electron equality does not hold. But for atoms, it does. So, all carbon atoms have 6 protons and 6 electrons. All nitrogen atoms have 7 protons and 7 electrons. And all oxygen atoms have 8 protons and, well, you get the point. Bottom line, change the number of protons in the nucleus and change the element, period. The second important number is the mass number. It is sometimes referred to as the A number. It is the sum of the mass of protons and the mass of the neutrons in a nucleus. Again, we're using the atomic mass unit AMUs. Since the mass of the proton in AMUs is 1 and the mass of the neutron is very close to 1, we can almost treat the mass number as if it were the number of protons plus the number of neutrons in the nucleus. At least at this stage of our learning, we will. We can use the helium from the periodic table as a further demonstration. The actual mass number for helium is 4.003, which shows that it's not really just counting the number of protons and neutrons. In fact, a quick check of the periodic table shows that most elements do not have a whole number for their mass number. We will delve deeper into this occurrence when we cover isotopes. For demonstration purposes, we'll go back to the 4 for the mass number. We see that the atomic number is 2, which means that helium has 2 protons. And we see that the mass number is 4, which means that there are 2 neutrons to go along with the 2 protons, since 2 plus 2 equals 4. The point here is that we can deduce the number of neutrons with an understanding of the mass number and a bit of arithmetic. This seems like a good time to test and review our understanding of the basics of the atom. Here we have a table with blank spaces for currently unknown values. We can determine these unknown values with a couple pieces of information and an understanding of the relationship between the subatomic particles, as well as the definitions we've covered in this lecture. Let's review what we know. The atomic number is the number of protons in the nucleus. The mass number is the mass of protons plus the mass of neutrons. We can perform a bit of mathematics on this equation and come up with a new equation that solves for the mass of neutrons. If we subtract the mass of protons from both sides of the equation, we get the mass number minus the mass of protons equals the mass of neutrons. Remember that atomic number is also the mass of the protons, which allows us to rewrite this equation as mass number minus atomic number equals mass of neutrons. A final step is to recall that neutrons have a mass almost equal to 1 AMU, so we can approximate the mass of neutrons as the count or the number of neutrons. That allows us to get the number of neutrons from the 2 important values in the periodic table, atomic number and mass number. And finally, in an atom, the number of protons equals the number of electrons. We can use nitrogen, as listed in the second column, as a test run and see how the table is compiled. Beginning with mass number. We can use its definition and its placement as the lower number or subscript next to the element symbol N. That's 14. Add 14 to the table. For atomic number, we can use its definition and its placement as the upper number or superscript next to the element symbol N. That's 7. The number of protons is 7. It's got from the definition the atomic number. Those two are equal to each other. Number of protons and atomic number. The number of neutrons we get from our modified version of the mass number definition. That's mass number 14 minus atomic number 7 to give us a 7 for the number of neutrons. And we can get the number of electrons from the equality of the number of protons to electrons in an atom. Since the number of protons is 7, the number of electrons is 7. That fills the column. Okay, let's try another one. This one is oxygen. Beginning with its mass number, we can use its definition and its subscript placement next to the element symbol O. Mass number is 16. For atomic number, we can use its definition and its superscript placement next to the element symbol O, and that's 8. We can get the number of protons from the definition of atomic number and is also 8. As for the neutrons, we use our modified version of the mass number definition. That will be mass number 16 minus atomic number 8 to give us 8 neutrons. And we get the number of electrons from equating it to the number of protons, and that is also 8. Now for a harder one. We can do the atom type bromine. This time we will attempt to derive mass number, atomic number, and number of protons from two pieces of information: number of neutrons, 44, and number of electrons, 35. In a sense, we will be working this problem set backwards. Since we have the number of electrons, we can use the equality relating protons to electrons. If we have 35 electrons, then the atom will have an equal number of protons, 35 protons. With this information and the definition of atomic number, we can add a 35 to the table for atomic number. We can also add that 35 to its proper place as a superscript on the symbol. What's left is the mass number. The definition says to add the mass of the protons and neutrons. The nice thing about using the AMU, atomic mass unit, is that 1 AMU is pretty much the same thing as 1 proton or 1 neutron. So the mass of protons plus the mass of neutrons can be treated as the number of protons plus the number of neutrons. 35 plus 44 is equal to 79. Our mass number is 79, and we can add this as a superscript to the atom symbol and complete the column on the table. One more. And this time we don't even have an atom type to start. We only have the number of protons, 26, and the number of neutrons, 30. Why don't we start by going after the atomic number? By definition, it is equal to the number of protons, and that is 26. At this point, we can head over to our periodic table and find what element is represented by atomic number 26. That appears to be iron, Fe. We can add the symbol and the atomic number superscript. Using the definition of mass number and the count of protons plus neutrons, thank you, atomic mass unit, we find the mass number to be equal to 26 plus 30, or 56. We can now add 56 as a subscript to our atomic symbol. And finally, the electrons are gotten from the equality of protons and electrons. If there are 26 protons, there are 26 electrons. What we have found in this exercise is that with a couple pieces of information and a firm understanding of the definitions and relationships between the subatomic particles, we can deduce or reason out the values of unknown quantities. With a bit of practice, this can become a valuable skill set. If you feel like you're on top of this table, then move forward. If not, back up and try these again. There is a lot here. Recapping the lecture. Atoms are comprised of 3 different subatomic particles. Protons have a mass of 1 AMU, atomic mass unit, and a charge of 1 plus or plus 1. Neutrons have a mass of approximately 1 AMU, but no charge. And electrons have a charge of -1 and a mass that is much, much smaller than the proton. In most cases, it can be ignored. In an atom, the number of protons equals the number of electrons. If they are not equal, we don't refer to them as atoms. Atomic charge is neutral. Atoms come in different forms or types. These are called elements and are collected in the periodic table of elements. One of the numerical values attached to each element on the table is its atomic number, sometimes called the Z number. It is the number of protons in the nucleus. The other important numerical value given is the mass, or A number. It is the sum of the protons and neutrons. Well, that completes the lecture, on the basics of atoms. Be sure to review the material and practice deducing the number of subatomic particles and the atomic and mass numbers.